Hi everybody, it's Ajanette and I'm here to go over your Chapter 2 lecture. This will be a kind of highlight reel of the lecture, so I'm going to go through it a little bit more quickly, and then if you want more detail you can go through and review the Zoom lecture in greater detail. So let me go ahead and put it in slideshow mode, and then we will go from there. Great. So in Chapter 2 we cover frequency distribution, and what we mean by frequency is we're counting the frequency with which a particular data point is occurring. So how often does it occur in the data set? When we're talking about descriptive statistics, our objective really is to simplify data, right? We want to organize it in a simplified way so it's really easier to kind of look at the data, get a general feel for the data. And so frequency distributions or frequency tables and graphs are wonderful ways for us to do that, because they give us a quick little organized table and or graph that tells us the range of data points and how many individuals or participants reported that particular data point in our data set. So it's a very quick and easy tabulation that you'll see, and it's a quick way of organizing our data. And so what you're going to see throughout this chapter is you're going to see there's two different types. There's a frequency table and a frequency graph. When we're talking about frequency tables, it's just columns and rows, right? And so it typically has two columns, one for the X value, which is actually the range of data points that occur in the data set. And then you're going to see the F column, which is the frequency, or how many times that data point occurs in the data set. We typically go from high to low, and so we put the highest values. Let's say you had a quiz ranging from 0 to 10. It would go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And then we'd say how many students scored each of those X values within that column. So it would look something like this. Now in this particular visual, it's showing scores from lowest to highest. The correct way is from highest to lowest, but keep in mind even SPSS does lowest to highest at times. And so, that's fine. I will accept either. But if you want to be correct, it's highest to lowest. Oh, so notice over here, we're scoring. This is the X values, right? So the score was anywhere from 1 to 10. And the F column, this tally is just giving you a visual to understand what a table is doing. It's counting how many participants scored that particular data value. And then the F frequency column tells you how many data points were in there. So when you add up all of the frequencies, this actually tells you your total number of participants. And so when we're looking at a frequency table, the best way to do it is really to practice. So I'm going to let you practice. So here is a set of 20 scores. This is going to be quiz scores. And you can see our lowest score is 4 and our highest score is 10. So the data points range from 4 to 10. And then you're going to actually count up how many individuals scored each of these particular data points. So the best thing to do is pause the video and then in your notes draft out what you think the frequency table should look like for this particular set of scores. And then what I do is I just start with the X column and then the frequency column, and then I actually will write up all of the possible values, and it looks like it was from 0 to 10 or 10 to 0 if you want to go from highest to lowest. And then as I am counting, like how many zeros did I have, how many 1s, 2s, 3s, 4s, I'll cross off those in my original set of data. When you're all done, it should look something like this. Now, notice that this doesn't include 0, 1, and 2, and 3 because those didn't appear in the data set. So it only includes the scores that actually occurred in the data set. That's okay, but if it's right smack in the middle, like 7, you would want to put 7 and then tell me 0. Don't break it up in the middle But if you want to start it at 4 because there aren't any lower scores, that's fine. Okay? And then you want to add, oops, I'm going to go back. You want to add up all these scores. So 2 plus 6 is 8, plus 6 is 14, plus 3 is 17, 18, 19, and then 20. And so we did have 20 participants. So that's just a way to double check yourself. And again, note that see, since 5 is in the middle, it included 5, and then put 0 for 5. Okay, so when we're talking about how are these used for calculation purposes, for computation purposes, sometimes we'll actually have you, do something, and this is primarily in this module, where you're going to have to do calculations, like you're going to have to do sum of x, or sum of x plus 1, or sum of x plus 2. And what it's trying to get you to do is just really understand what is the data that you're working with. Honestly, though, we don't do a lot of this, but it's prepping you for the next chapter, which is measures of central tendency, where you are going to have to do x minus the mean and then square that value in order to calculate measures of variability. So in any event, what you want to do when you're talking about doing a sum of x from a frequency distribution is you have to be careful, because the frequency table itself, right, sometimes we just want to sum up all the x's, and that's not true, because we had 2 10s and 6 9s. So we actually need to do x times the frequency. So 10 times 2 is 40, 9 times 6 is 54, 8 times 6 is 48. And then we add up all those, and that is the sum of x. So we want to be really careful that we're accounting for the fact that this frequency table is telling us there were 6 8s, there were 6 9s. So when we want to use a frequency table to do sum of x, the most common mistake is people focus on the x column and they forget about the frequency column. And you can't. You have to really create a third column. And that's not uncommon, where when you start with a basic table for computational purposes as you're doing various statistics, then you'll go ahead and you will add columns that allow for these new formulas. And same thing with x minus, sum of x squared, right, is first you want to square each score, and then you want to sum them as many times as it occurs, right? So again, if I had 2 10s, I want to square x, or square 10 first. So 10 times 10 is 100. And then I want to, now I have 2 of those hundreds. So sum of x squared for just 10 is 200, okay? Okay, so here it's going to give you some practices. And so you can go ahead and pause the video, and here for this particular data set, it's got scores of 1 through 5. There was 1 5, 2 4s, 3 3s, 3 2s, and 1 1. It wants you to calculate sum of x. You can't just add up all these. You actually have to add that third column and do what I suggested. You also need to take into consideration a new column for x squared, and also times that times frequency as well. So here's the first example, so here's an example. So sum of x, again we have 1 5, 2 4s, 3 3s, 3 2s, and 1 1. Or you can do 5 times 1 and create a second column, right? 4 times 2 is 8, 3 times 3 is 9, so on and so forth, and sum that all up. For x squared, you can do 5 squared, and then again there's 2 4 squared, and 3 3 squared, and 3 2 squared. So you cannot forget the frequency, okay? And so here's your answers. Okay, so let's talk about other features that you might see on frequency tables. Sometimes you'll see a proportion, a column, and it's F over N. So it's what it's telling you is it's telling you the proportion. So of this, if we go back to our original example, in this quiz, what percentage of students or what proportion of the students scored a 10, scored a perfect score? 2 of 20. So 10% of our students scored a perfect score. What percentage scored a 9 or an A, even though it wasn't a perfect score? They still scored an A. And so that would be 6 over 20, right? So you might just add a column here that's a proportion or an F of N column that tells you the proportion of participants that account for that particular data value in your overall data set. And so we're looking at 100%. Oh, excuse me. You can then make that a percentage, right? So I would have F of N where it's my proportion, where 2 of my 20. And then I could add a column that's P of 100, which is now the percentage. And so that's, I'm going to actually do the math now and convert that to 20%. So these are commonly seen in your SPSS tables, and they can be super helpful, particularly when you're trying to analyze a particular data table or output, where you're looking at it and you're saying, okay, it looks like over half of my participants are represented in this range of scores. And that might tell you something depending upon what kind of data you're looking at and what type of research question you have. So I find the proportion and percentage columns can be really helpful at analyzing your descriptive data. So like in this case, 50% of our participants, of our respondents were white. Now, depending upon the corresponding population, that may or may not be representative, right? And so you want to kind of look at how does this sample represent the larger population from which we're trying to draw conclusions, right? Because it may or may not generalize. And so we want to be mindful of those things. Or, if I'm, doing a question on, Roe versus Wade, or, women's reproductive rights, if my sample is all men, well, then that might influence the responses versus if I'm including women, right? So I need to consider those things depending upon the research question. So let's talk about group frequencies. Now, we were talking about quiz scores from 0 to 100, from 0 to 10, and that's a smaller range. Remember, the purpose of descriptive stats is to really simplify and summarize our data in a quick, easy way, so we can just quickly look at it and get a feel for the data. Well, let's say you had an exam score and it had 100 points possible. Well, now we have all those data points. And that's a lot, and it no longer becomes a simplified version if we outline every single possible score. So instead, we want to group them, and we want to create class intervals. And maybe I'm going to say everybody that got, in the 90 range, 80 range, 70 range, 60 range, and I'm going to group those, and I'm going to create a class interval. That still allows me a quicker way. Now, I lose some data, right? I don't know how many people got a low C as opposed to a high C, so I do lose some data, but it does make it simpler and easier for me to organize the data still in a very kind of clean table. So rather than the individual scores, we focus on intervals. Now, we do have kind of a set of rules that we want to follow, because the question is, well, how many intervals should I have? How big should those intervals be? And the answer is, well, it depends, right? So our rules of thumb that we're going to follow is you want to keep it to 10 class intervals or less. All of the width of the interval, or the amount of possible point values in each interval or group, should be the same, right? And it should also be relatively simple. So it should be divisible by like 2, 5, or 10. So it's easily countable. So we quickly can see the organization, and if we know the first 2 class intervals, we can easily calculate and discern the next. The bottom score, so the lower limit of that group, should be a multiple of the width, right? So again, stick to 2s, 5s, and 10s. It's easier. And all intervals should be the same way. Okay. So let's take a quick look. Here's a practice set of scores of 25 scores. Quickly just look at the low range, your low score. So it looks like your low score is 53. And let's quickly look at our high score. So we're talking about 53 to 94, I think. And so that gives you a good feel for about how much data do you need to account for, right? And if I'm shooting for class intervals of 10, I can say, okay, I can have a width of 5 values in each score, or I can just go ahead and do 10 and have it have fewer groups, and that's okay too. But remember that the more scores accounted for in the groups, the more data I'm losing. So if you want to go ahead and pause my video and take a crack at it, go ahead. Otherwise, I'll show you if I went with the 5 range, right? Then I'm going to start again, even though you had 54 as your lowest score up here. I thought it was 53. 53 is your lowest score up here. You can't just put 53. The width has to cover a range of scores, and the range of scores needs, the same number of scores needs to be included in each interval, right? So I'm going to start with 50 to 54. I had 1 score fall within that range. 55 to 59, I had another score fall within that range. Notice that I lose data, like I don't know it was a 53, I just know the score fell somewhere between a 50 and a 54. Same here. 60 to 64, notice that they're all 5 points, they all cover 5 points, 50, 1, 2, 3, 4. 55, 6, 7, 8, 9, they all cover 5 data points. I don't have any more than 10. We can quickly discern that they're 5 data points, so they're easy multiples to go by, and that makes it a really easy graph, an easy table to discern. And then when I still count up my frequencies and I sum all these up, so 7 plus 5 is 12, 16, 19, 20, 23, 24, 25. I had n equals 25, so I know I accounted for all my data points. Okay? Okay. So let's talk about real limits. So real limits can be confusing for people, but it really applies for continuous variables. Like money, we can break down. You don't just have $5, you may have $5.52, right? We can break it down into an infinite number of possible values. If we have, a pie, we can cut it into 3 pieces, 6 pieces, 9 pieces, 10 pieces, so we can continue to cut it down. And remember, we use histograms with continuous variables, and those bar charts those bars are touching, representing the fact that there's really no gaps in between them. They can be broken down into smaller pieces. And so consequently, when you have a continuous variable, you want to create limits, because we want to say, okay, what falls into that category? What is the range of scores? So if I'm going to say you have $10, but you really have $9.98, $9.75, what's that marker before I say you have $9 or $10? $9.50 or $10. So I want to be mindful of setting those limits, right? And our real limits are those boundaries where we say you're either in this or you're in this. And those boundaries are touching. There's no gaps, just like with our histograms, okay? So it is the real limit separating those adjacent scores. Now, apparent limits we use for like our group frequencies. We created those class intervals, right? So they are typically whole numbers marking the beginning and the end of any given interval. And so when we create frequency distribution graphs, you're going to have 4 different graphs that you commonly see. A bar graph is used for nominal data or ordinal data. Remember, nominal data is different just in name only. There is no quantitative difference or value difference in each of the scores. They're just different, okay? Men and women, chocolate versus vanilla, they're just different. Ordinal is they're different, but they're also ranked. First, second, third place. They don't have equal distances between the ranks. So when we have nominal or ordinal data, we are going to use bar graphs. And that's really important, especially when you're doing your SPSS work, because you have to decide what graph to use for your data set and your research questions. So you have to really pay attention to what are we asking, what type of data is it, and based upon that, what type of graph do I use. Histograms I use for interval or ratio data. For continuous variables, I'm going to use a histogram. For discrete variables or nominal data, I'm going to use a bar chart. Now, modified histograms are still histograms, but then I get to see the frequency within each of the bar charts. So it gives me a little bit extra information visually. I don't have to estimate it or try to see where it lines up on the y-axis. I can just visually see. And polygons, instead of using bar charts or bars, they use lines. And so polygons are not commonly seen in our data. Just so you know, we don't use them a lot in this class, but you might see them in the research and the literature. So when we talk about a bar chart or any kind of graph, you have an x and a y axis, and our x-axis is the horizontal axis, and our y-axis is the vertical axis. So here you're going to see this is our x-axis, and this is our y-axis. So our x-axis is usually what we use to establish our categories, our boundaries, and the y-axis is where we would put the value or the frequency, right? When you have nominal data, notice it's a bar chart. They're separate. They're not attached. And you use that anytime it's non-numerical data or it's qualitative differences. Notice the separate bars indicate that they're separate and distinct categories, okay? So you leave that space intentionally. Histograms, notice that these are all touching, okay? So it's like a bar chart, only they're touching, they're kissing. Why? Because this is representing interval ratio data, continuous variables, where they can be broken down into smaller and smaller parts, so there are no gaps, right? But the width of the bar itself extends to the limits, to the real limits associated for that particular category. So if I said you have to have somewhere between $9.51 and $10 and $10.49 in order to be in the 10 category, if this is the $10 category, this limit is going to be the $9.51 or $9.50, and then this limit over here to the right is going to be the $10.49. Okay, no gaps, no gaps. Okay, and a modified histogram, again, the bar charts the bars are touching, okay, but it gives us a little bit more data, and then it breaks the bar up into chunks, and so we can count the frequencies or how many data points were in that particular group, okay? And then a polygon, again, instead of using charts, it puts a dot at the frequency, and then all the dots are connected by lines. Not as commonly seen, but still very much something that you might see in the research or the literature, okay? So when we're talking about population data, we rarely have data on the entire population, right? What we know about a population is because we've taken samples and we use that to estimate quite often. Sometimes we absolutely do know all the data about the population, but not always. And so there are circumstances where we might have to do a relative frequency graph. So take, for instance, I don't know how many fish are in the pond. I don't know how many of them are trout and how many of them are, I don't know, salmon. But I know that after fishing for 2 hours, people typically catch more salmon than trout. Well, that can tell me, I can use those ratios to tell me, relatively speaking, so for this example, it's giving you bluegill and bass. I don't know exactly how many bluegill or how many bass are in it, but I can say, relatively speaking, I typically catch about half as many bass as I do bluegill. So I'm going to assume relatively there are twice as many bluegill as there are bass. A normal distribution is a very special kind of distribution. It's going to be foundational for the work that we do in inferential statistics, but it's a very, very specific. It means it is precise. So when we use the word normal distribution, it is a perfectly symmetrical distribution. The mean, median, and mean all are in the middle. They all equal one another. There's 50% of scores below and 50% of scores above, and it breaks up into this perfect intervals where I can say about 70% of the entire population falls within one standard deviation, and then about 95% of the population falls within 2 standard deviations. And we know for IQ scores that it is a perfectly normal distribution. Of course, we need to take into consideration that there is a lot of racial bias built into the development of the IQ scores and assessment of intelligence overall. So we often are relying on these kind of archaic measurement tools that were built early in our field when there was still a tremendous amount of systemic and scientific racism. And we still see it, if I'm being honest with you, right? We still see it. We see it in the medical field. We most definitely see it in a number of areas. So know that it's still there. But from a mathematical standpoint and a statistical standpoint, IQs are a really great tool to kind of visualize a normal distribution because we have a fair amount of knowledge and data on IQ tests, as biased as they might be. So when we're talking about the shape of a distribution, it tells you a lot. And you need to pay attention to your data set. When you run a bar chart and you put the curve over the chart, or a histogram and you put the curve over the chart, you're looking for skewness. You're asking yourself, what is the shape of distribution? Is it a normal distribution where it's perfectly symmetrical? Now, it can be a symmetrical distribution and not normal, just so you know that. Like, for a normal distribution, the mean, median, and mean all equal one another. Okay, so you'll get into this further in the subsequent chapters. Not all symmetrical distributions are normal, but all normal distributions are symmetrical. You can also have skewed distributions, where it's positively skewed or negatively skewed. Now, the difference is where's the tail. So the tail is opposite of the big mountain. Okay, so here's our big mountain, and it's lined up on the positive end of the line. And then the tail is going to go off and tail off into the negative end of the line. So this is negatively skewed. So typically what happens is you had a lower score that have leaned more toward the negative end of the number line. And when you average it all out, it pulls the mean to the left, okay? In the same circumstance, you might have lower scores and then one super high score, and it pulls the scores to the right toward the positive end of the number line. And so we call that negatively skewed and positively skewed. And that typically is indicative of some sort of outlier. And we have to be careful when there's an outlier, right? Because we need to know that that mean is being pulled. It's artificially saying that it's higher than it is. We're trying to assess our income levels of our students, and we just happen to have, some movie star kid in the class whose income levels is significantly higher. It's going to pull the scores and make it seem like we all have higher income levels than we really do. So we have to be mindful of the shape of the distribution. So make sure you're paying attention and you're analyzing that. So this is just good practice to figure out if you can identify what's positively skewed, what's negatively skewed. So I'm going to encourage you to pause, write those answers out based upon these practice problems, and then restart. And what you're going to find is this is a fully symmetrical distribution. It looks like a perfectly normal distribution. This one is positively skewed because the tail is being pulled to the positive end of the number line. And this one is negatively skewed because it's being pulled to the negative end of that number line. So when you're thinking about, and this is going to be really helpful for your SPSS module homework, you have to look at the data. You have to know how to follow the instructions and input the data into SPSS. When it's nominal data, you have to assign it a code. Those codes are arbitrary because they're just qualitatively different from one category to the next. But you are going to decide, okay, if I'm doing a frequency table, does it need to be a regular frequency table or a grouped frequency table? What range of scores do I want to include? But you do have to be able to assess that, based on the data and make some decisions. Based upon the scale of measurement, am I going to use a bar graph or a histogram? Pretty much we'll never use polygons. You'll always use a histogram. And then you're going to have to determine your intervals. So when you are going to use a grouped frequency. And I'm going to tell you, interestingly enough, SPSS will do it for you. So here's some practice problems that you can work on just to make sure you're understanding the content. So in addition to watching this lecture video, make sure you're going back and you're doing your reading, and then you're working out the practice problems as you're going, and you can answer these effectively, okay? And so here is a resource to help you determine when to use what graph. Again, the scale of measurement matters, so it's really important you have that content down from chapter 1. And then, again, for our purposes, we'll use predominantly bar graphs and histograms, okay? And then let me know if you have any questions, and I am here if you need me, so just reach out. Bye.